All right, so I wanted to do an interesting application of this idea of center of mass. At the end of chapter 9, we were looking at the idea that a system of particles can have a center of mass. And we can also apply Newton's second law to that assembly of objects if they're moving together and sort of predict their motion based on the motion of their center of mass. It turns out that when we look at Newton's second law, we can rewrite it in terms of, for instance, the acceleration of the center of mass. And so that we can say that the sum of the external forces acting on the system, now that neglects the forces within the system, so if the objects are exerting forces on each other, those are action-reaction pairs which will cancel out. So we'll be only left with the external forces. And so those sum of those external forces will be equal to the total mass of the system times the acceleration of the center of mass of the system. Now, one type of problem that we can use or apply is the idea where individual pieces of the system will move, but because there's no net external force, the center of mass position will remain the same, and that can help us solve for some different types of problems. So in this problem, what we have is we have a woman. She has a mass of 45 kilograms, and she's actually standing 1 meter from the end of a 5 meter long, 60 kilogram canoe. We're going to assume, of course, that the canoe is uniform, so we can say that its center of mass is located at its center. So she's standing here 1 meter from the end. She's going to actually walk to the other end of the canoe, and she's going to stop 1 meter from the opposite end. Now, I think we might expect that as she's walking, the canoe will be moving sort of in the opposite direction. We could think of that as sort of a momentum conservation. That's one way to think about it. But we could also think of it from the point of view as she walks forward, she has to exert a force backwards on the canoe. And so the canoe will be pushing her forward to propel her, but she'll also be pushing the canoe backward. However, those two forces that I'm talking about are internal to the system and will cancel out, and so we don't count those as external forces. Now, in this scenario, if we just ignore the fact that the water will offer some resistance to the movement of the canoe, and we just neglect that, we want to answer the question, how far does the canoe move? Now let's come back to our Newton's second law, but in terms of the center of mass. In this scenario, I don't have any net external forces. This is in equilibrium. Remember that I said that the force that the woman exerts on the canoe and that the force that the canoe exerts on the woman, those are internal forces, they're an action-reaction pair, and they will cancel out. Well, if the acceleration of the center of mass is 0, that means that the velocity of the center mass is actually a constant. Now, because it was actually equal to 0, then that means that the center of mass position becomes a constant. So that regardless of how she moves and the canoe moves, the center of mass of the system will remain the same. We're going to use that to figure out how far the canoe has moved. So I already drew my initial scenario of what things look like, and I put the end of the canoe at my x equals 0. And now I'm going to imagine the canoe will move backward, so I'm going to sort of put it back like this. This is the distance that the canoe has moved. I'm not really sure how far that is. I'm going to figure that out. The entire length of the canoe is 5 meters, and the woman is now 1 meter from the end, as we were told. This means that this distance for where she's located now is actually going to be 4 minus x, because the distance from the end of the canoe to where she stands would represent 4 meters because she's 1 meter from the end of the canoe. But we're not counting this x distance. So this is just going to be 4 minus x. Similarly, the center of the canoe is going to be measured as 2.5 minus x. Okay, so those are the positions of both her and the canoe. So let's find out what the initial value of the center of mass is for this scenario. So we had the mass of the woman times her position plus the mass of the canoe times its position divided by the mass of the woman and the canoe added together. So she was 45 kilograms. She was located a distance of 1 meter from the x equals 0. The canoe is 60 kilograms, and the mass is located in the geometric center of the canoe, which is 2.5 meters from the end. And then we're going to divide by the total mass of the woman and the canoe, which is 105. This ends up to be 195 over 105, which is equal to 1.86 meters. So the center of mass of the system is 1.86 meters, and we expect this to remain the same. So after she walks, we expect that to be 1.86, but we have different values to go into the calculation. We have the mass of the woman, her position, mass of the canoe, its position, and then the mass of the canoe plus the mass of the woman. But now this time, remember, I already labeled like where she is and how we could express her positions and the canoe's position. So we still have 45 kilograms, but now we say she's at 4 minus x. And we have 60 kilograms, and that's at 2.5 minus x. And that's divided by 105 is the total mass. So I'm going to set that equal to 1.86. So I have 1.86 times 105 is equal to 45 times 4 minus x plus 60 times 2.5 minus x. And so that's the algebraic expression that I need to solve. This is going to give me 195.3 is equal to 180 minus 45x plus 150 minus 60x. And so then we can solve this for x. So I think I'm going to skip some of the steps because I'm running out of room, and I think it's relatively simple algebra. I end up solving for the x is 1.28 meters. And so as she walked forward, of course the canoe moved backwards. She walked forward 3 meters. The canoe moved back 1.28 meters. Seems reasonable, but the basic idea that we used to solve this problem was that the center of mass of the system was going to remain where it was because of the fact that there was no net force on the system to cause it to move, to accelerate it, or to give it any velocity. And so that allowed us to figure out where exactly everything would be after she walked to the other end.